we can take it in the future.
So what is this tool? Well, it's a tool that's designed to just be able to run and execute EVM logic with full parity as quickly as possible. So we do this by interfacing with the Rust implementation of the EVM called revm. This is something used in the RETH client that's being built, as well as being used in Anvil. And what we're trying to do here, at least in our current implementation, is be able to simulate price processes, price action, and things like this with smart contracts for DeFi. For example, we can build stochastically generated price paths and also include multiple different kinds of agents that each have their own kind of predefined traits. For example, something like an arbitrageur or maybe like retail traders, and watch them interact with this sort of composable, build it yourself environment that you want to test with. When we do this, we're going to be able to record all the output we get from these simulations and also give you a way to post-process all this data that you get, visualize it, and maybe start to do some statistics with it as well. Furthermore, we want to make this tool very general so that you can do something in the simulation environment and take it and actually use that and interact with real running networks, mainnet or layer twos and things like this. So we have abilities to like filter and display logs that come out of the Ethereum mainnet, watch these logs and have agents, act upon them in this way. They can see historical data and take this into account as well, and then bundle and send transactions on chain.
So why did we want to build this tool? You may have seen some of the capabilities and you may be thinking, oh, there are some existing tools that can handle some of these capabilities. We found that something that checked all of our boxes wasn't quite there and wasn't performant in the way that we wanted it to be. And we are kind of initially motivated because something about Colin and I, we maybe regrettably came from academia, and so we are very curious, which is very good. And so we wanted to study smart contract vulnerabilities. We wanted to examine the concept of evaluating mechanism design and mechanism strengths and weaknesses, and auditing mechanisms in a greater ecosystem environment composable with other systems. And this means that we're going to need both back testing and forward testing. And we wanted a strong degree of granularity to build out our performant feature set, as well as composability in our ecosystem design. So, we wanted to be able to deploy any number of arbitrary contracts and kind of leverage quote unquote EVM God mode to put them in the state that we want. And then performantly analyze our simulations. So with that, I'm going to hand it off to Colin, who's going to walk you guys through kind of a nice example of Arbiter's current capabilities.
So I want to start this off with something that we're all going to be intimately familiar with at this point and, bordering on seeing too many times. But that's actually kind of the purpose of, battle testing, a simulation tool that is used for testing. So let's think about Uniswap V2. This is, as far as we know, a very battle-tested and great protocol. We don't expect to see any bugs from it. But fortunately, since we're running these contracts directly, there's chances that we may find, interesting bugs that could pop up. If we're swapping against this or, adding liquidity over and over again, and we end up finding some weird state from some weird price path or something like this, or just like unexpected reverts or anything like this, we might see them here. So we're looking to see if anything like this pops up. On the kind of financial side, we have this belief that Uniswap V2 is maybe a generalist, not optimized for certain kinds of strategies that one, may want to implement. For instance, maybe we want to do some kind of volatility harvesting or something like this on a stable pair, say USDT and USDC. So in order to test these hypotheses, what we need to do is set up an environment that's going to let us see what happens. So we can set up with a single pair of tokens. We call them something like, Arbiter token X and Arbiter token Y. And then we have a single Uniswap pool that we deploy and we initialize and allocate to. And then we also have this dummy contract that we call the liquid exchange. This is a contract that kind of has no price impact when you swap against it. This makes it a nice testing tool. And it's also the tool that allows us to seed prices into this environment for the arbitrageur, our agent that's going to run in this setup, to see and find differences between this liquid exchange and the Uniswap pool and go ahead and send an arbitrage trade to bring these two prices back into alignment with one another. It's a very classic scenario here. We're going to be able to see, and record the performance and how much gains the arbitrageur and the LP can make over time. We can see all the price action take place and watch what happens. So to configure this scenario, what we're going to do is use a price process called the Ornstein-Uhlenbeck process. This process is something that is mean reverting. So if I say, hey, the mean price should be 1, which we expect with stable tokens, these stochastic processes are going to kind of bounce around the price of 1, but always stay pretty close. It's going to look like what a stable token price will do. We're going to set, say, some capital T amount of prices that we're going to run over each price path. We're going to do M different paths per process that we're going to do here. So per seed of process. And then we're going to say vary over capital N different parameter sets per process. What this is going to give us is M times N distinct different scenarios that run, and a total of M times N times T price updates that allow us to see, hey, are there any reverts or anything like this as well, right? So over on the right, I'm just showing you, from my own terminal, what this looks like to run. You can just say, hey, Arbiter, I want to simulate this Uniswap simulation. You hit enter, and lo and behold, even running, say, about 100 different simulations with 1,000 price processes, it took 1.4 seconds, and we get some output. Given this output, we want to be able to visualize it at least, right? Make sure what we're doing is making sense. Does our arbitrager even arbitrage properly, right? That would be a concern. If we look at this over on the left, this is recorded data from this exact simulation. What's happening on the left is the liquid exchange is changing price, and the Uniswap pool is also changing price because the arbitrageur is swapping against both in order to make a little bit of profit here and there, and to also equilibrate the two pools or two exchanges back to the same price. Because there's a continual amount of these swaps occurring and fees are paid to the LP via Uniswap V2's 30 bips fee mechanism, the LP that is providing liquidity to this pool is earning fee revenue over time. So we can see over on the right that we're tracking the reserves, both the X token and the Y token. These are bouncing all over the place, right, as the arbitrageur is swapping. But what we can find kind of consistently throughout this is the amount of liquidity that the LP itself is holding on to is steadily increasing over time as trades are occurring. This is everything we expected. We don't see any bugs in Uniswap V2. We didn't expect to. None of us here did, right? But we're seeing the kind of performance we expect. And if we wanted to compare this to, say, some other kind of more optimized exchange, maybe Uniswap V3, or products that Primitive might be offering in the future, then we can do that as well.
Nice. So with that, let's take a little bit of a step back and start to take a look at the design decisions we've made and kind of the performance that we've seen so far. So if you were wanting to use Arbiter to design your own simulation, there are kind of 3 steps with 3 kind of sub-steps on the last step. The way we have architectured the tool right now is you install your Git submodules first, and this is done with Foundry's Forge install. I'm sure many of us here in the audience know and love Foundry. We did this to allow Arbiter to handle any arbitrary smart contract repository and work with those contracts as they seem fit. Next, we generate the bindings, the Rust bindings for the contracts. Under the hood, this is being done with Forge Bind, but we kind of have an abstraction over these with our bash script that we have. And then from the Rust bindings, we have a nice interface over the contract ABIs, and we can kind of design our simulation. So the kind of 3 steps that you're going to want to do when you do design a simulation is, first off, you're going to want to deploy all of the contracts that your simulation will interact with. Next, you're going to want to send all of your initialization calls. These are going to be things like token approvals or mints. This is going to allow you to put the state of the Rust EVM in the desired state that you would want it to be to start the simulation. And then the last step is determining your agents and the price processes that you want to run your simulation against. And this can be done in a config file that we have put together an example of how to use that, which is pretty nice. So with that, let's step into the simulate crate.
So the simulate crate has been the primary focus for us over the last, say, like 3 or 4 months. It's the largest crate, and everything we've talked about this far kind of falls into this, except for all the like command line interfacing that we do. For example, things like the price processes that we're talking about all live inside this stochastic module, which we plan on adding a bit to in order to have other agents that also behave stochastically. So further plans there. Example, like retail traders can be quite stochastic. All the traits and behavior of agents are going to go inside this agent module, and we're going to continue to add there quite a bit as well. Now, the contract and environment modules here, these are really just to interface with revm, the Rust EVM, and they're just to allow us to nicely deploy contracts, know that they're deployed, where they're deployed at, all of this. And the environment is kind of really just handling transaction and the database requirements that we need in order to track state change. Historic is a bit of a newer module for us that is going to let us interface with back testing data, so historical data. And wrapping it all up, the manager is kind of the god of everything here. They take control of all the agents, the environment, and allow these 2 entities to work together and to actually run simulations that you just saw with our example.
Awesome. So taking an example of kind of the performance in the forward testing example that we've shown, we've been able to process over 1,000 swaps per second, unoptimized, so this is just like with the dev compile environments. And this is on some data just from our 2 different stochastic price processes. And in the future, we want to add maybe some jump diffusion to our stochastic price processes so we can simulate some larger volatility events as well. When contrasting this with what Anvil is capable of off the bat, this is a huge performance increase as far as many orders of magnitude of swaps per second. So moving in here, the repository architecture of library is fairly simple. We have at the top level directory, 2 primary directories are contracts. This is where our Git submodules will go. You can install any Git submodules here. And then we have our lib. And our lib is where we have our simulate crate and our on-chain crate. And then, of course, we have the Arbiter binary that leverages these resources. So moving into some comparisons, I'll let Colin take it from here.
So we kind of commonly get asked, like what's the difference between this and other tools out there? And by and large, I think the kind of most similar software you'll see out there are what Gauntlet and Chaos Labs are working with. Now, those are not open source tools. They are, giving themselves away as a service. And they, to some extent, also don't announce exactly all the features they have. So, and for example, like with historical backtesting kind of stuff, we're making a guess here. I wouldn't be shocked to see it, right? But we don't totally know, or at least I don't. Now, we are using a tool like Foundry alongside us. We're using it with Forge. We might be using it in other ways in the future as well. But Foundry is not really a comparable tool, and it doesn't really aim to be. It's not designed to just let you do forward testing or, use backtesting data to run any kind of simulations, let alone kind of agent-based simulations. What is out there that is probably the most similar and what people are building on top of as well is ApeWorks. It's a wonderful open source project that does allow you to build on top of basically like an Anvil interface. So you can be running contracts directly and sending transactions as if they were going to a live chain. And from this, you can kind of build forward testing suites. You can go back and on your own grab historical data. They don't necessarily give you a way to do this, and there's nothing wrong with that. And to my knowledge, they don't have any agent-based tooling simulation, equipment themselves. However, what I should say is that there are groups that have been building really nice products on top of ApeWorks. I am forgetting some of the names at the moment. I can share them after this talk, but they are building kind of back testing historical data, analysis, as well as forward testing. An example would be, say, Elementify is doing this, and now it's coming back to me. I think Small Quants has some nice ApeWorks projects in the works as well.
Awesome. So looking forward, let's take a little bit of a look of like what we've been doing to build Arbiter and where we kind of want to like go with Arbiter. So in the beginning of this year, we spent the majority of our time building scaffolding around revm so that we could interface with revm the right way. This was a little bit of a learning experience off the bat. We definitely figured things out the hard way a couple ways here. And then we just finished kind of the end of Q2, bringing the simulations to live with some of the example data that we were able to show you guys, which was a huge crux. So we're super stoked to kind of be over the primary MVP, the primary feature set here. Moving into Q4 and Q3 of this year, our kind of goals are to really, take care of some of our technical debt and work with different teams and individuals on using Arbiter so that we can really improve the usability and the test coverage of the repository. And then in Q4, we're going to be focusing on shipping new features, stuff like new agents, stuff like ecosystem modularity. I believe there are a couple other great tools in the ecosystem that I think Arbiter could work really well with, as well as some post-processing tools for better kind of statistical analysis and visualization. That being said, we did build Arbiter open source from day one. We definitely wanted to showcase our like learning experience in building the tool. And it's certainly really important for us to like interact to the greater community and build tools that are not just useful to us, but also useful to a lot of other people in the ecosystem. I think there's a lot of opportunity to really improve tools like this. Right now, Arbiter is pretty young, and I know that there's many different ways we could improve it, and I'm sure a lot of people in the audience even know things that I'll probably never think of on how we can even improve it from there. That being said, Colin and I have personally spent a lot of time and energy making the repository open and accessible to new contributors. We spend a lot of time trying to really well document our issues, always keep up a variety of good first issues, and are more than happy to talk to anybody who's interested in contributing to the project or desires a specific feature that would be useful for their specific use case. We definitely care about the greater ecosystem at large. Now, wrapping things up, there are a few frequently asked questions, and then we'll definitely answer some questions from the audience. The first three I'm going to kind of answer all together with varying degrees. The first three questions that we get a lot is, can you fork mainnet and upload its state into revm? And the answer to this is actually yes, and it's actually not too difficult. However, we have not designed a feature around this, so it is something you do manually. There's a nice example in the revm repository maintained by Dragon, which is kind of a great example of how you might want to approach doing this. As far as adding this to the feature set of Arbiter, I'd say this is kind of high on our priority list. So we're certainly invested in making kind of an abstraction around this feature so that it's very easy for people to use. Can you model block space? Yes, you absolutely can model block space. I think that the really nice part of interfacing with revm directly, in contrast to a higher level of abstraction, maybe something like Anvil, is that we really have a fine granular control over what we can do. So nothing's really outside of our reach as what we can design and build. The question is just how difficult it is to ship that feature and how much of a priority should it be. The same is true for building complicated simulations. We have kind of modularized this process somewhat in the current state. However, it's kind of our goal to increase the usability and ease at which users could design these simulations. The last kind of question we get is like, oh, who are the primary users of Arbiter? And I think that I think of four people when I think about this. I think of sophisticated financial actors for on-chain activity. So this is stuff like searchers. This is stuff like different funds. People doing like real statistical arbitrage where you need to train your models on a large quantity of really high quality data. Another user that I see a lot is mechanism auditors. I know that there's a ton of like really bright people here in the audience. You guys are all involved with the Spearbit ecosystem. Spearbit does amazing audits. They've done some amazing audits for us at Primitive. We're super fortunate to work with such brilliant people here. But even with formally verified contracts, there's some risk that you might want to analyze. And this is a tool we see Arbiter being really good for. And then in addition to mechanism designers, if you're building your own protocols, this might be a tool that you really want to use to incorporate into your development lifecycle. So maybe you are building some smart contracts or some system, and you want to evaluate how the features that you're adding perform iteratively. This is a way to we see shorten the testing to production pipeline and kind of give people a lot more confidence that their mechanisms are behaving as intended. And then lastly, we have been contacted by some academics in the space from IC3 at Cornell. And I foresee, as our industry continues to mature and grow and become more and more studied in the academic domain, that there will be people wanting to use Arbiter for that as well. So this is our last slide. So with that, I'm going to conclude. Thank you guys all for listening, and we do have some time to take some questions. Maybe take a look at the Q&A here.
I got to pull that.
Yes, thank you. If you look at the top right, there is a button on Discord.
Nice.
Is the chat there? Yeah.
Yeah. So some types. Did we have any issues with types, with the primitive types mismatch? So we did initially, absolutely. And some of you may remember there was some breaking changes with ethers, like 3 or 4 months ago that also were really challenging for us. However, that being said, we've spoken to Dragon and Georgios, and it seems like we're converging on a singular types library, and we're doing the best to always use the latest stable versions. Next question here. What are the kind of stuff you can do that is more granular than when using a higher level tool like Anvil? So I think one thing we really have a huge edge of is this many magnitudes of performance increase allows us to build kind of scenarios that would be impossible to model with rigor for smaller scoped simulations. Having about between 20x to 200x speed and performance when contrasting Anvil is really, really big. I think some other things that we can really do here is our back testing and forward testing is not something that's outside of the box shipped with Anvil. Anvil's a really amazing tool, and I think ApeWorks does a really amazing job of building some of these features around Anvil. However, we didn't want to be limited by the I/O of sending requests, so we really wanted to go a level deeper and get revm directly, so that we could really, leverage the performance of this. And maybe Colin has something to say on this as well.
Yeah, I feel like you kind of touched on these like two last questions that are currently posted. Fran, a little bit more on that. Maybe one thing someone could consider doing, I've thought about doing myself, is like maybe you want to play around with some kind of sequencing rules and you want to play around with like, block ordering or how you want to do blocking and things like this, for example. Since revm is just an execution environment, there's nothing stopping you from kind of like constructing blocks, sequencing ways you want them to be, or even kind of attaching, your own form of consensus to this that you might want to be studying yourself. Those are other kind of possibilities as well. And then the next question too was kind of, how much performance does this actually introduce over Anvil? Yesterday, I was running a script that just made 1,000 reads from Anvil. It took my computer about 20 seconds. Now, I have not done anything to optimize this. I have not played with many settings or anything like this to try to make it go faster. I did have instantaneous mining on, of course, so there was no, block times. I didn't put 20-second block times. I'm not, evil. But like this morning and yesterday, I was running a simulation of ours that has 1,000 swaps, actually 1,000 arbitrages, which means there was like, roughly speaking, probably, a few events to parse and then actually a few calls to make, not just two swaps, but other calls that involve, seeing how much to swap and things like this as well. Those 1,000 swaps, they are a lot faster. And that was with so like 1,000 swaps in a second, 1,000 reads from Anvil in 20 seconds. That's like a roughly, 20 times speed up. And then this morning I was playing around with it, used like the release binary instead, and found that was maybe about 10 times faster. So I'm not going to claim, any true to form benchmarks at this moment, but I would expect orders of magnitude faster.
To add on that, one thing we'll definitely do moving forward is do like a more rigorous analysis of performance and speed. And you can look from us, and we'll add something there to be available to the community with concrete ways of how to reproduce the benchmarks as well.
So the last question I also see up, I'm not going to try to pronounce your name. I kind of want Percussion. So really interesting question you're asking. And the thing that comes to my mind first and foremost is we're deep in our own audit with Spearbit. And there's, findings that they've found. And we ran into in trying to test our own protocol's performance actually in this like stable pool scenario with a bug with our swap performance. We were finding that like once you do a few swaps, something weird happens that causes our invariant to just like, in essence, go negative, which it shouldn't. And so we found a bug in our own contracts just by trying to interface, a simulation with it. So it's kind of, it's almost funny in a way. Technically, the simulation itself didn't, catch this, but trying to build one did. And this is what I really like about this kind of approach, ApeWorks taking it to, is that we're running contracts directly, right? That means we're testing them at the same time. We're not just building some kind of like, Python replica, which our team has also done for our protocol, but the Python replica doesn't catch bugs. So yeah, hopefully that answers that question.
And this is actually was also a finding that the Spearbit team found and documented quite heavily as well. Is this tool mostly used for economic reviews? I think it certainly has a lot of strength being used for studying economic performance, maybe performance of different arbitrage, whether atomic or statistical, or LPs, or different portfolio rebalancing strategies, as well as evaluating economic risk on black swan events, with huge volatility events. However, I do think that because it is so performant and it is so fast, you can absolutely use this to expose other anomaly behavior that is perhaps more of a defect with the implementation and a security vulnerability. So I do believe that while you can audit the mechanism design security, that because of the pure performance and throughput of the tool, it is also a valuable tool for evaluating the security of the contracts. And yeah, Rust is amazing. I think this project is largely due to Colin and I falling in love with Rust.
Yeah, Arbiter is really a love story after all.
Yeah. Nice. Thanks for linking the repository. Any recommendations of what stochastic processes work well in the context of DeFi? Absolutely. I'm going to let Colin talk about this because he's jumping up and down right now, and his math background's really strong.
I mean, we've actually talked at length about this with a good friend of ours. His name's Elijah. I don't know if he's here. He's probably not here, but that'd be kind of funny. But anyway, he's like honestly, question like what even the use of like testing stochastic processes against this is. But I'm thinking of that because your question's a good one. Like, is geometric Brownian motion actually a good test in the context of DeFi? And the answer is like over long periods of time, markets don't actually behave like this. Volatility changes over time. Drift can change over time. Geometric Brownian motion is really like a linearization or like, the sort of tangent space of a market. It's really useful for studying like short bursts, or maybe you really want to test contrived scenarios. There's actually nothing wrong with testing contrived scenarios. On the flip side, the example we gave you here today with the Ornstein Uhlenbeck, this is actually really great for testing something like a stable token. And maybe you want to test a stable token, right? And you want it to perform, over time, but maybe you want to add some kind of big price shock in there, right? Like a depeg event. Well, this is something we can add in addition. Like, I'm not going to say like, oh, right now you just hit this button and it's a feature, but it's something that you can, modify throughout. So you could change, the volatility at some moment in time from being say like 0.01 to being 0.5, right? A 50x increase. This is going to give you a lot of chaos. I will also mention we talked very, very briefly about like jump diffusion processes. These are actually quite nice for like testing price shocks. Gauntlet, I know, uses these for a fact. And I'm also going to shill one of our teammates who has been really growing in her capabilities as a developer, is a fantastic researcher. Her name is Estelle. I bet she's here listening. And I think she would love to talk a lot more about like stochastic processes for simulations and things like this. And to drag this on a little bit further, there's processes like Poisson processes that model wait times, for example, which would allow us to have kind of retail agents who sort of trade, stochastically over time and with, kind of stochastically chosen volumes and things like this as well. When Monte Carlo simulation support depends on what kind of Monte Carlo simulations you're looking for. Yeah, let us know. Start a discussion. That would be good.
I think as of like right now, it's really important to Colin and I, as the maintainers of Arbiter, that we actually listen to the community on what to build. So say you want Monte Carlo simulation support, open an issue and we'll ship it for you, because we don't want this to be something that like is only useful to a subset. We think that we can really build this to be super valuable. Fran, did you write some really low-level assertions, such as testing for access memory or some weird behavior? We have a variety of tests. Admittedly, our test coverage right now is pretty low. We've kind of been sprinting to ship this MVP here. I think over the next quarter here, our focus is going to be on a lot more testing. Fortunately for us, because revm is being used in the RETH client, it is very well maintained and is pretty well tested as well. So this is a great kind of utilization of a dependency that is becoming pretty critical to the greater ecosystem. If you don't know about revm, definitely check it out. It's basically the EVM stack machine written in Rust by Dragon, who is an absolute horse of an engineer and an amazing Rust person, active person in this community. Colin just showed the link here as well. Yes. Searchers and arbitrageurs, I think, are going to be a very interested in this, mainly because of its performance and the quantity of data that it is able to produce with EVM parity. Um, Being able to model that level of that quantity of data that has that high degree of quality is very important. If anybody's familiar with high frequency trading in traditional finance, and like what goes into statistical arbitrage, that may be more obvious to them than it is to other people.
Another point on that, it's part of the backstory of Arbiter was actually rooted in MEV and LP performance. Part of why we want people to be able to build agents and deploy them, in a simulation environment and then to a live network is for things like that. You may have seen like Artemis, which was launched by Paradigm. Yeah, that came out recently. And to some extent, like that sort of implementation is something that we're also, very curious to be working with as well.
Yeah. Um. Uh. Anyway, we're super happy to talk to you guys today, and Colin and I are definitely available and can be reached in Primitive's community Discord, as well as on the GitHub. If any of you guys are wanting specific features or wanting to contribute, just open an issue or start a discussion, or even just DM us. We're more than happy to talk more.